Ok, pues ya estamos acá. Vamos a escuchar la plática de Manmohan. Él está en cuarto cuatrimestre del doctorado de la CES. Y bueno, pues le damos la palabra a Jan. Jan, please. Start, please.
Sí. Gracias. Can I speak in? Can I give my presentation in English?
Yes.
Okay. Muchas gracias.
Yeah, you are starting.
Okay. So my name is Manmohan Jain, and today I am going to present my advance of my thesis. And the title of my work is the exploration and the optimization of nanocrystalline silicon oxycarbide based materials for downshift conversion and their application to solar cells. This is the table of content of my today's work, which I am going to present. So first I will give the introduction of my work. As we know that the world's population is increasing day by day, due to which the demand of energy is also increasing very rapidly. Besides it is also a very important issue to reduce the greenhouse gas emission. For this purpose, renewable energy can play a vital role to gain both these above goals. And if we see the contribution of solar energy till 2019, then it is only 3% of total global energy. If we see the limitations of crystalline silicon solar cell, then Shockley-Quisier's model explain that the maximum achievable efficiency of crystalline silicon solar cell is only 30% with the band gap of 1.1 electron volt. Another research group of Richard et al. Explained the main losses in the crystalline silicon solar cell, which are thermalization loss, transmission loss, and recombination loss. And Trupke et al. Explained the solutions of these losses, which are down conversion, up conversion, and photoluminescence downshift conversion, respectively. Here we will focus on the recombination loss, which can be overcome by photoluminescence downshift method. So these loss occur in the surface of crystalline silicon solar cell due to the high energy photons. So first we will see the cause of poor UV response, as we can see in external quantum efficiency near to 300 to 400 nanometer wavelength. The external quantum efficiency is very less. So the reason of this is the shallow absorption depth of UV photons, which increase the probability of recombination of generated carriers with the help of surface defect state. And this is one of the reason of reduced UV response. Except it, refractive index of
Jen, ¿escuchan ustedes?
Sí, se fue el sonido.
Ya se cortó, no se oye.
Pensé que era el mío.
Se cortó el sonido.
Me parece que Manmohan tiene el micrófono apagado.
Ah, ok.
Yes, yes.
Okay.
I don't.
Okay.
So I have explained about this slide, or I need to explain again?
Repeat the last slide, please.
Okay.
Yes, the problem is I hear it by pulses, so it's very difficult to understand.
Okay. From here.
Please speak a little bit loud, please.
Okay. Okay, I will try to speak aloud. According to Shockley-Quisier's model, it explained that the maximum efficiency of a solar cell is only 30% if the band gap is 1.1 electron volt. Another research group of Richard et al. Explained the main losses in crystalline silicon solar cells, which are thermalization loss, transmission loss, and recombination loss. And Trupke et al. Explained the solutions of these losses, with the help of which we can improve the efficiency of solar cells up to 37%. These solutions are down conversion method, upconversion method, and photoluminescence downshift method. Here we will talk about the recombination loss and the solution of this is for photoluminescence. Here recombination loss happens due to the high energy photons which recombine very fast in the surface of silicon solar cell. First, we will talk about the causes of poor UV response here. So here we can see from 300 to 400 nanometer of external quantum efficiency in the figure that the response is very less. So the regions of this is the shallow absorption depth of UV photons, which increase the probability of recombination of generated carriers with the help of surface defect states, and this reduce the UV response. Except it, refractive index is very high in this UV region, which further reduce the UV response because it increased the reflection. Due to high refractive index, the high dispersivity is also very high, which complicates the optimizing at anti-reflection coatings. If we talk about the photoluminescence mechanism, then Oval et al. Proposed the downshifting method firstly for the UV photons to convert it in longer wavelength to increase the efficiency of solar cell. The phenomena of absorption of photons and subsequent emission of light is termed as photoluminescence, as we can see in the figure 3. If we talk about the characteristic of PL downshift mechanism, then we can see in the figure number 4 that downshift method only modifies the solar spectrum to the better match light absorption properties, and it does not modify the intrinsic structure of solar cell. So it only increase the F current of the solar cell, and while the voltage remain constant. So in this way, the quantum efficiency should always be less than or equal to 1 for downshift method. So if we talk about the approaches to get this kind of method, so there are two approaches, very general. First, to deposit a rare earth materials layer in the front face of photovoltaic device, and the another is the to grow a oxide, nitride or carbide layer by thermal or PECVD to passivate surface defects in order to reduce the front surface recombination velocity. Here we are going to use silicon oxycarbide because it have so many advantageous properties over oxide and nitride matrices. As we can see, it have more good chemical properties, mechanical properties, and it is also compatible with in silicon-based ICs. It have tunable refractive index, thermal and photo stability, wide band gap, better creep resistance, and low gas permeability. If we talk about the deposition of silicon oxycarbide thin films and its material tillite, then it have deposited with monomethylsilane, dimethylsilane, and these materials which I have shown in this list with the help of respective systems. So with the help of this list, we can see that so many groups have deposited silicon oxycarbide thin films till yet, but the photoluminescence, the properties of photoluminescence have not studied very widely till yet. And in our group till yet, we have deposited the silicon oxycarbide thin films with the help of TEOS and MMS gas till yet. Here we are using MS and TOS gas because silane is a very toxic and flammable gas, and it is also very explosive. So it is better to use organic materials like MMS and TEOS gas. The full form of MS is monomethylsilane, and its chemical formula is CS6Si. With the formula, we can see that the ratio of carbon content in silicon atom is 1:1. while in tetraethyl orthosilicate, TEOS, the chemical formula of this is C8H20O4Si. As we can see in the chemical formula of TEOS that all the necessary atoms are present in this chemical formula, like silicon, oxygen, and carbon. So we don't need any other precursor for in this system. And if we will see the carbon content, the ratio of carbon content in silicon atom, then it is 8:1. If we will talk about the probability of dissociation of entire molecule, then it is very high in MMS, while it is very low in TEOS. So in MMS, we get more silicon carbide like silicon oxycarbide thin films, while we get the silicon oxycarbide thin films which are more silicon oxide like in TEOS method. So that's why we are using two separate kind of materials here. If we will talk about the previous work of our research group, so first I will tell about the OCAT CVD. Firstly, the formation of silicon oxycarbide thin films were confirmed in our group by using TEOS material in 2014. And in 2018, we published in another paper in our group in which the effect of working pressure were explained. And with it, they also explained the effect of hydrogen and oxygen annealing treatment. In 2019, the region of the PL emission was also explained with the help of quantum confinement effect. With the previous work, we can observe that the effect of varying temperature, deposition duration, and flow of organ gas in the deposition of silicon oxycarbide thin films is not discussed till yet. Moreover, the effect of nitrogen annealing and various plasma treatments have not also discussed till yet. If we talk about the SWCVD system, then in 2017, the deposition of silicon oxycarbide thin films were reported with the help of MMS and oxygen precursor. In the same paper, the effect of the variation of oxygen gas flow were also observed. In 2019, another paper was published in which the region of photoluminescence were explained with the help of PLE technique, in which they explained that it is due to the defect related mechanism. And here also we can see that various effects, the effect of various parameters have not studied very well till yet, which we can do with the help of annealing and plasma treatment also. So the objectives of my work is to explore and optimize the nanocrystalline silicon oxycarbide based materials for PL downshift conversion and their application to solar cell. Another objective is to develop silicon oxycarbide thin film using tetraethyl orthosilicate in OCAT CVD and optimize parameters of deposition by understanding their film properties. The third objective is to develop silicon oxycarbide thin film using monomethylsilane and vinylsilane and oxygen as source gases in SWCVD and understand their film properties. Here I want to say that last year we were using MMS gas and it were finished. So now in the future we will use vinylsilane. So I have not explained about vinylsilane till yet, but in the future I will explain about this also. After this, we need to also investigate the mechanism of the PL emission in the silicon oxycarbide thin films. And in the end, we need to also study the effect of heat treatments and plasma treatment in the properties of thin films. So this is my proposed methodology. First, I will use the deposition systems of OCAT CVD and hot wire CVD. And then I need to do characterization of these various characterization for structural, morphological, and optical study, and then collect and analyze the data. So here firstly I will discuss about the results in that OCAT CVD deposited thin films. Here in the figure, I have shown the OCAT CVT system which I have used in SIS department. And here I have used only one precursor, TEOS, while the filament is tungsten wire. Here I have used silicon P-type silicon substrate for deposition, and here I have used the parameters according to my previous literature of my research group. So these are the constant parameters, like substrate temperature is 200 degrees centigrade, working pressure is 0.30 torr, initial vacuum is 0.08 torr, and filament temperature is 1800 degrees centigrade. So here I am showing that in the table I am showing the refractive index and thickness of deposited samples, and here we can see that refractive index is not constant and it is varying for every sample. So here we can see that the addition of organ flow changed the kinetics of the CVT process, and the Brownian motion of organ atoms changes the diffusion and convective flux of molecules, which reaches to the hot filament. Except it, during the deposition, the composition of the thin film changes due to some bonding. Then subsequently, our refractive index also changes. Moreover, in some cases, the temperature of the substrate sample is gradually raised in chamber due to hot electrons hitting the substrate, and this is also one of the reasons which change the composition and morphology of the film and its direct impact on the refractive index. If we will see the FTIR spectra, then we can see here at the absorption band at the wave number of 1100 centimeter inverse, there is a peak of silicon oxycarbide thin film, and another peak is near to 1060, and it is shifted from its stoichiometry value of 1080 of silicon oxy-silicon bond. We will talk about more about this shift, the effect of this shift in the next part. And here we can see the content of silicon height SiH bonds, SiC bonds, and CO2 bonds. And here in the XPS spectra, we can see that the availability of silicon, oxygen, and carbon spectra, which confirms the presence of silicon oxycarbide thin films.
¿Ahorita la están viendo?
Hello?
No, please continue.
Okay. Yes. So here we can see that silicon, oxygen, and carbon is present in the thin film. So it confirms the presence of silicon oxycarbide thin films. Here in the table we can see that SiO3, SiO2, C2, SiO3C bonds are present in very good percentage. So we can see that this is we have achieved silicon oxycarbide thin films in our substrate. Except it, now I am going to discuss about the PL spectra of my samples, and we can see here in figure number 10 that there is a very broad PL emission spectra from around 380 to 700. In which we can see saturated spectra from 477 nanometers to 550 nanometers. So the region of this spectra around 477 nanometers are explained here. First region can be the shift in the silicon oxygen silicon bonds as shown previously in FTIR spectra. As we can see here in figure number 11, that when the silicon oxygen stretching vibration bonds shift from its stoichiometry value, then it also changes it generates a higher probability of having one or more silicon neighboring atoms, and it can allow to control the intensity of luminescence and its spectral composition. Besides it, silicon and carbon ion or and silicon carbide nanoclusters can also be the region of photoluminescence in this region from 2.7 to 2.5 electron volt, as shown in figure. Besides itself, trapped excitons defects also discussed in some papers for a possible mechanism in this for this PL emission. Now I will present the I will discuss about the results of SWCVD. The image of hot wire CVD is shown in the figure 12, and here we use monomethyl silane and oxygen gas as a precursor, while here we use tantalum wire as a filament and silicon substrate. Here also I have used the parameters according based on the literature of our research group, and here also I see the variation of the time deposition. Here the flow of hydrogen, oxygen and MMS gas is 21 and 4. So here we can see again the refractive index and thickness of our samples. Here we can see that the thickness and refractive index both are very changed in comparison to OCAD CVD. The refractive index is 1.7 to 1.77, which shows which can be due to the use of different material like MMS, and because we use here monomethyl silane gas, so the probability of dissociation is also different than TEOS liquid. So that's why it can be one of the reasons for the change in the refractive index and thickness. And yes, here the refractive index is more higher, which show that the more silicon carbide related bonding, because the refractive index of silicon carbide is 2.63 and the refractive index of silicon oxide is 1.45. So here we can see the FTIR spectra of deposited samples. Here at again at 1100 centimeter inverse wave number, we can see the silicon oxycarbide absorption band, and another silicon oxygen absorption band we can see at 1025, which show more high shift in his stoichiometry value from 1080. So as we have discussed previously also, this shift may generate a higher probability of having different atoms, and in this case the carbon bonding atoms probability can be high. Except it in FTIR we can see SiH, SiC and CO2 related bondings which are presented at 670, 800 and 2290 centimeter inverse wave numbers. If we see the XPS results of this 30-minute deposited sample, so here we can see that all the silicon, carbon and oxygen also available here. And if we see the table, that here we have we get the silicon carbide atomic silicon carbide related bondings also here, which confirm our previous theory in which we discussed that MMS have more silicon carbide related bondings and properties of silicon oxycarbide thin films. Here we can see photoluminescence spectra of deposited samples, and here we can see that it is the peak of the photoluminescence of these samples is around 2.2 electron volt or near to 500 80 nanometer. This peak is related to the emission. This emission is due to the hydrogen-related species like silicon oxygen oxyhydride or silicon hydride-related defects on the surface. Except it hydrogen, we have seen in FTIR spectra that already there is a higher shift in the stoichiometry value of the silicon oxide bonds, which increase the carbon-related defects mechanism in PL emission. So here we can see these are the conclusions that the formation we have confirmed the formation of silicon oxycarbide thin films with the help of FTIR and XPS results. We have also discussed the role of organ environment in the chamber of OC activity, which is important because it may change the flux of molecules and that reaches the hot filament. Except it, the thin film deposited in hot wire CVD instruments show high refractive index in comparison to OC CVD. This can be due to the use of different materials like MS and TOS and their dissociation processes. And the PL emission can be different, can be due to the different defect mechanisms like oxygen-related defects, hydrogen-related defects, carbon-related defects, or STE, self-trapped emission. Or it can be also due to the quantum confinement effect, which we need to study in the future. To investigate the regions of PL emissions in silicon oxycarbide thin films, we need to study further PLE, total emission and HR10 characterization, which are important to get the PL emission regions. So my future plans is to develop the silicon oxycarbide thin films using TEOS and with the help of TEOS and vinyl silane for the downshifting of solar cell application and understanding their film properties. Also analyze the heat treatment and plasma treatment in the hydrogen or oxygen and organ environment. Except it, it is also necessary to analyze the effect of different configuration of tantalum wire and tungsten wire, like zigzag kind of configuration, circle kind of configuration. And to know the PL emission, it is necessary to do more analysis like TRPL, PLE, and HR10. These are the references of my work. And thank you so much for Skonasit to provide me regular beca, Cinvestav to provide me lab for Cinvestav and Unam to provide me lab, and thanks to all professors and my colleagues to help me and support me for all work. Thank you so much.
Okay, Jen, thank you very much for your presentation.